All right, Mr. Ferro, part two. We need
Part
to
two.
discuss quality of experience and what that is. Now that we're done dumping all over diffserv and QoS and RSVP and all these things that, as you say, don't work. Well, they do kind of, as we established in
Yeah.
the previous video, but near enough and good enough. Can't we do better? And
Yeah.
you've got some thoughts here.
Yeah, well, I think one of the interesting things is, just before I get going here, one of the interesting things about QoS is that QoS was hugely valuable when bandwidth was less than 2 megs. And I remember chatting to Fred Baker about 10 years ago, and he said once we get beyond 2 megs, QoS doesn't actually work all that well. Processing the QoS takes longer than it does to just thump the packet out the other side. The delay you inject can be negative. Now, that was an era when processing packets was very slow, and it's slightly different today. But here's the thing.
Control plane
Right?
CPUs were quite different then, but yeah.
The best way that we can give principle of least astonishment to the users and give them a robust, predictable user experience is bandwidth. If QoS isn't predictably stable and isn't cost effective when you come down to it, you're giving no guarantees at enormous cost, at enormous complexity that's a very weak and unpredictable, unstable to a large extent, then really the only answer you've got is bandwidth. So the more bandwidth you throw at something, there's two things that happen here that a lot of people don't understand. As you increase the speed, you're also increasing the size of the pipe. So if you go from 50 meg to 100 meg, you're doubling the size of the pipe, but you're also reducing the latency. So you're actually, as you increase the size of the pipe, you also increase the clock rate, and that reduces latency. So more bandwidth doesn't just have one impact, it has multiple impacts, right?
But bandwidth doesn't solve everything. The thing you haven't talked about are microbursts. And no matter what, no matter how much bandwidth you have, just due to the nature of tiered networks, you are going to have small amounts of time where a downstream interface gets congested. For example, 40 1 gig ports filling a 10 gig port, a 10 gig port filling a downstream 1 gig port, and these kind of things. So there is an argument to be made, even in the case of massive amounts of bandwidth and paying the big bucks for the bandwidth, that you could use a QoS policy of some sort.
It can, but what many people forget is that TCP and UDP flow control is designed to specifically handle that use case. Now, in the data center, there's a viable use case there because microbursts can cause problems in very low latency environments. But in high latency environments, microbursts are a trivial corner case. That is, in a WAN where the latency gets over 50 milliseconds, a certain number of packets are expected to be dropped, and TCP flow control or UDP flow control in the app expects that to happen. That is not something that necessarily should be handled in the network layer.
TCP, definitely right. You will have, in the face of drops, TCP is going to back off. That's how it's designed to work. UDP, you're screwed. And so if in a use case like VoIP, then you would need to consider, is this a use case where I must have QoS and guarantee that quality of experience for the user?
So in HTTP2, the UDP flow control algorithm is actually looking at the latency of the end-to-end.
Yep.
So as the latency changes, and this includes, how long it sits in a buffer and so forth, it adapts so that packets don't get lost. So in a sense, we're moving away from the old model of don't drop packets so retransmissions don't happen to newer, more modern protocols that monitor for that itself and adapt the flow rate, the transmission rate of UDP and TCP. So that is the heart of the modern era. QoS becomes less relevant as time goes by.
And lots of the modern TCP variants are exactly about that as well, yes. In addition to HTTP2, as you mentioned.
Right. And this improves the experience, the user experience improves, but without having to be concerned about QoS in the network. So again, this is modern apps using modern protocols reduce the need for QoS going forward because of that, right?
But again, use case specific. I just want to remind people of that. You love to speak in the terms where it's like it's all this now, and it isn't always.
Yeah. You've got to understand the difference between a niche or a corner case or an exceptional case. So if you want to talk to me about voice, that is a trivial use case. If you look at the overall usage of the internet, voice isn't all that important. Now, it might be to you if you run a contact center, in which case all bets are off. And if you think that voice quality is a really important thing, which I find kind of weird because everybody talks on a mobile phone where voice quality is entirely optional, right? A handset, right? This is not designed to take a voice call in here at all, in any way, shape, or form. It's the worst possible. That's why the old handsets were curved, right? To put the microphone in front of your mouth. Where's this put it? Puts it right. So if you think people care about a voice call, you're just seriously.
If anyone calls me for a voice call, it's like, you savage, use text like a human. What's wrong with you?
Yeah, that's right. I actually had to talk to my bank today. They called me, and then right afterwards I got a message saying, we forgot, Mr. Ferro, you said you don't answer the phone. I don't actually answer the phone. Right. So I think the interesting thing here is that if we think about bandwidth, if you can just get more bandwidths one way or the other, you can start to think about, well, how do I scale bandwidth? Now, one way to do it is to scale vertically, which is what we've always done for the last 20 years. So if I've got a 50 meg, I'll upgrade it to 100 meg. If I've got 200 meg, I'll upgrade it to a gig, whatever the number is, as much as the market will bear. The challenge here is that scaling vertically is very expensive. The ability to step up means that you commit to a single vendor. What you really want is the option, at least, to have many small bandwidths. So instead of having 500, would it not be better to have 5 by 100s and then get them from multiple providers and see if that works out cheaper?
Well, hang on a second. Not just cheaper, but more robustly, because you said something very key, which is a diversity of vendors. That matters a ton.
Yes. So what did we just see today? There was a blog post published today by Michael McNamara. He's saying that he was buying an MPLS service from AT&T, and somewhere inside of the network, Verizon was providing the tail. The service went down. AT&T said, after 3 hours of checking the network, said it's not us. And then 4 hours later, Verizon got in contact and said they deprovisioned the circuit. So why wouldn't you just connect to Verizon in the first place and not deal with AT&T and go through the quality of these providers is pretty variable. In this situation, the business was down and he couldn't go back to the business and that this very expensive WAN that he had was worthwhile. So you would be better off with many small bandwidths from multiple suppliers, reduce the cost per line. Now, there is a difference here between tail circuits and bandwidth. If you've got a 1 gig tail, it could be cheaper to have a 500 meg on a 1 gig tail instead of having 2 1 gig tails and 2 200s or whatever the number is.
And let's not forget, that we're talking about from an engineering perspective. Dealing with multiple vendors from a business perspective is annoying. It's a pain in the rear end. So some people are going to be put off by that. But anyway, right. I get your point.
Now, the reason we don't do many small bandwidths today is because with destination-based routing, like we do with BGP and OSPF, you can't do that.
It's too hard.
You only have a single best path. So part of the reason most people wander around going, I just have to get more bandwidth to solve this problem, or I'll fiddle with QoS instead of solving the problem fundamentally and thinking it through. I would be better off having 4 100 megs than 1 500 meg or an active standby. What about if I've got 2 200s? I would be better off with 4 100s, because if one failed, at least I've got 300. Because if I've got 2 200s, I'm only going to get 200.
To go back to your BGP point, when you're outbound, you'll end up with some spread over those links, probably, assuming they're all coming from comparable tier. But you can't control it. It's not an even distribution. But just in case people think that, if I turn on BGP, I'll only be able to use one of my circuits outbound. Nah, you'll be able to use more than one, assuming you're taking in a full load of routes from everybody.
If you've done this and you've done that and this works, but if somebody's actually transferring a full rate flow, that circuit will be overloaded and that one won't. And like if you've got an A circuit and a B circuit and you're doing load balancing, and if someone's going out this one, they might saturate this link one and this one will be entry. That's very common when people start talking to the big public clouds and they transfer files out. They'll saturate one link completely, and anybody who gets loaded into that link, done. You get a brownout situation, and BGP doesn't detect that.
It does not.
So again, not very good. The limitations of the network technology that we have, that everybody runs around going, it's fine, we just put load balancing on, it works. The people keep forgetting that these fundamental flaws here, right? And again, internet bandwidth's not guaranteed. Your upstream provider might not be guaranteed. Your MPLS provider is highly unreliable. So if we assume that multiple low-quality bandwidths work better than one, then what is it that we have to do to take address? Why isn't we haven't done that up until now? We have to go back to our principle of least astonishment, which is it must not, it just must work predictably.
You don't want to use it on notice, pretty much. Yeah.
That's right. So we must be able to switch between circuits without the user noticing. That means not flow balancing. If you're going to flow balance, like manage a flow of an application between 2 points, you've got to be able to say this one's overloaded, so I'll load balance onto this one. In the old days, you could do flow balancing by locking one to A and B, a bit like an MLAG. They do an XOR on the MAC header, and if it's 0, it goes to the left, and it's 1 goes to the right. It's not even load balancing, and it's not based on the load being generated. The second thing is that edge devices must be able to observe application performance and respond at will. So they need to be able to self-configure and adaptively reconfigure themselves in the network without user interventions.
In other words, in reaction to changing network topology, whereas typical routing protocols and their calculations don't really have any intuition about load on the network. They only know how they're interconnected, and you end up with a best path computation based on that, as opposed to what you're describing when we're getting to the SD-WAN scenario, what these different vendors do, where they're taking measurements across different paths, and depending on the real-time measurement results, jitter, drops, latency, it can look at a flow that is it needs to send out, know what the real-time condition is of those multiple links are, and then make a forwarding decision. The policy for this particular flow is X. And if I send it out link B, I'm going to be able to meet the SLA assigned by that policy, which is something we've never been able to do before. We've never had the complete or on edge devices to be able to
No.
pull that off.
No. And take it a step further. So there are some SD-WAN vendors that will actually do per packet load balancing, and they'll actually do it per direction, which is very important in the case of broadband circuits, which are asymmetric. You might have 200 meg down and 20 meg up. You've got an entirely different traffic profile and cost strategy going this way than you do coming in. And if you've got 4 outbound circuits and 4 inbound circuits, you've actually got multiple ways of balancing in either direction. Ideally, let's just assume this is an ideally hyperbolic, imaginary conversation. You actually want to be choosing the 4 outbounds entirely separately from the ones coming back the other way. The cheaper SD-WAN vendors say, we monitor the performance of the link, we pick A, B, C, D, and then they lock the flow to that.
As opposed to a path where they're actually monitoring effectively through a tunnel. They're monitoring through an overlay path. And they've got a full mesh of overlay paths between the 2 different edge devices. They'll stand up the full mesh, monitor each tunnel. Now they've got full ability to monitor any combination of in and outbound circuits and make a decision that way.
Yeah, and we could talk about SD-WAN vendors. What do they do to monitor those circuits? Like the really cheap, low complexity solutions just use BFD. Send a BFD either end, and if it comes back quickly enough and it comes back, the circuit is up and it's not browned out, right? So it's not under stress. Well, that's not very good. What you really want to do is you want really intelligent analysis of the application. So you want to be aware that this is database or web surfing or Facebook or, this is my business critical app or this is YouTube. And to be able to say mission critical, not mission critical, regardless of the parameters, right? This is not IP address. This is based on metadata, based on a database of information sitting in the device, intelligently understanding the network from an applications perspective. Got nothing to do with packets, nothing to do with cross tags or buffers or whatever. The whole principle is about deep packet inspection and knowledge of the application. And that's where the user comes in. That's where the quality of experience idea comes in.
Yeah, the big idea here, we want packets to be forwarded across the WAN in such a way that, going back to your principle of was it least astonishment? We want the user to have that application perform very well. And again, going back to the whole root of this conversation, Greg, when you're trying to do that across the public internet and trying to use old school tools that just haven't worked in the best of circumstances all that well, applying them to the internet's a non-starter. So you need to have a system that can do active measurements and apply that to an application in order for that to work, or your user experience is going to be unpredictable. It's the quality of experience and being able to guarantee that user experience is a consistent one in the face of a potentially wildly changing bandwidth and WAN situation.
And that's right. And I'm talking about 4 paths, A, B, C, D. So if line C suddenly gets congested in the upload direction, well, I'll just start using one of the other 3. It won't have any problems. And in fact, the more you scale horizontally, the better the performance gets because you get more path options, more path choices, right? The circuit can be congested because there's a big fat upload going up it. The circuit could be congested because the DSLAM that it's going to is congested, or maybe if you're on a PON type tail circuit, you still have to know what the physical network is behind these things. But there's no reason why you can't go, set up in a premises and have a 4G, 5G connection, a DSL, a cable, and an MPLS, and use all 4. Or have multiple MPLS DIA.
If people do. We know that those scenarios exist. It depends on cost and use cases and a variety of things. But yeah, we know that people mix up circuits exactly like that without a network engineer having to sit there and go, how should I build the routing policy so I can actually leverage these? Oh, I got to make sure this fails over like I want. Oh, do I have my OSPF adjacencies nailed up the way I expect, and or DMVPN meshed up through? You don't have to have that excruciating thought process that gets more and more difficult to scale as you add circuits and bandwidth to the mix.
There's a couple of things that you need to take away here. One of the things about SD-WAN and this quality of experience is monitoring of the network performance is table stakes. So, bandwidth here, that's the real key in these new environments is analytics. You have to have application performance as the starting point. Because if you can't monitor the application performance, I can't guarantee the user or the CIO that this is any better than QoS on a routed network. I might as well not do anything. Does that make sense? So I have to have analytics engine. And the good part about analytics is I can do it for the first time because this deep packet inspection engine that does application performance monitoring is built into the SD-WAN edge.
Yeah, just the fact that there's inspection, deep packet inspection going on implies you can pull a lot of metadata out and get some pretty interesting analytics and reporting out of it. Yep.
And so then you have a cloud app, which then gathers up the analytics data in some form. Usually it's a polled, as and when bandwidth is available, it gets pushed up to the cloud, and then the charts or everything are done for you. The second thing that you get from all of these smart devices then is visibility. Not just the old monitoring thing, up, down, whatever. You actually start to see all the assets in the network. You get config management, you get zero-touch provisioning, you get, all that stuff that we used to buy as an add-on just becomes table stakes. Again, because the edge is intelligent.
It's application-centric on the bandwidth side as well. And we've had that in some tools before, but I know a lot of basic network management systems that are SNMP heavy. You just kind of see a lot of numbers and percentages, and it's not getting a great application mix. Even if you're using flow exporters, you get more detail of what's really going on to where with a modern SD-WAN system.
But all of a sudden you've got asset management, configuration history, logging, all the logging's taken care of in the SDN app that comes with SD-WAN. There's a whole bunch of accessories that come here.
I mean, it depends. There's a wide diversity of SD-WAN apps, and they don't all have all of that stuff.
No,
but yes, I get your point. Yeah.
Maybe we'll go into a part 3 here, because I think there's a few things about quality of experience, some of the nitty-gritties. Do you want to hit those in the next video?
Yeah, we're going to take a break here and catch us in part 3. And we're going to
part 3 about one part video.
We swear.